Okay, so far in this series of lecture on hashing demystified, we have so far covered basic definition of hashing, hash table, and hash function, the collision birthday paradox, and hash table doubling in chaining, load factor, complexity of table doubling, which seems to be order of n, but it's actually order of 1 in amortized sense. And today we will cover the universal hashing and perfect hashing. Okay. And this lecture will be followed by more advanced hashing paradigms like cuckoo hashing and Bloom filter. Okay. And we will see some cryptographic hash functions. Okay, so let's start with universal hashing and perfect hashing. So what is universal hashing? Before going to universal hashing, let's understand the mapping hash function better. Okay. So what we have a set of elements, okay, and each elements are actually key value pair. Each element is key value pair, and the hash function works on key and its map to a hash table. We can denote it by T and length is n. So range of the function is lies between 0 to n minus 1, and we have n number of keys here. K1, K2, we have n number of keys. So we have to map this n number of keys to the this given range, okay, given range of the table. So this function is defined to satisfy that condition. Okay. Now to understand better this function, we have to first understand the key space. Okay. How many possible keys are there in the key space? How many possible keys are there in the key space? So let's say these keys are, for example, p bits. P bits long. So what will be the space? The key space will be 0, 1 to the power. Okay. So all possible string of length p. Okay. That will be the. So what will be the size of this key space? Size of this key space is 2 to the power p. Okay. There will be 2 to the power p number of such keys. Now this set does not contain all the keys, all the 2 to the power p number. 2 to the power p is basically very larger than n. Okay. This is all possible keys, and among those key space, some smaller subset. So this key space can be written as the, let's say this is our universe U. U is the universe of key space. So from this universe, we have to pick some keys, and we have to pick n number of keys, and we are not. This is not in our hand. This is this depend on the problem and the data. What will be the key? Okay. So is small subset from the universe is taken into the domain of the hash. Okay. So while choosing this hash function, our objective is to map the element independently in this table. What does it mean? Suppose we are mapping two elements HKI and HKJ. Okay. So suppose we have inserted HKI, then we are inserting HKJ. So is this HKJ, value of this HKJ is independent of HKI? If this happens, this is a good hash. It should be independent. Okay. If there are dependency, then that is not preferred. So rationale is this hash function is actually defined on this universe. So basically the hash function is defined on universe to 0 and minus 1. Okay. So if you were giving a subset, yes, subset of U, it is most of the time proper subset. So I am omitting, we can keep also, no issue. So basically this is a subset of U, and from this for this S we are using, but this function is actually defined on the universe. Okay, and we have to define the function in the universe in such a way that it can choose the range independently, choose the output value independently of the previous. Each draw should be independent. So that should be a good as well. So it will be more clear to you if I give you some example of bad hash function. Let's say hx equal to 2x more than. Okay, hx equal to 2x more than. What will happen? Any idea? So whatever the key value, it will always become even number. Okay, it will always become even number, and if we map this, then all the odd position will be empty. Okay, odd position will be empty. So this is not a independent function. Okay, so every position should have equal probability. If I am inserting here, then it should have probability 1 by m. If I am inserting some element here, it should have probability 1 by m. Okay. So if we are able to create some function in this way, which is maintaining uniform probability throughout the table for every insertion, then it is a universal hash. Example of a universal hash function is, we can write, let's say hx equal to ax plus b mod b mod m. Okay, what is this p? We should write q. We have already used p here, so I am writing q, where q is a large prime number. Why large prime number? Because prime number does not have any factor, and whatever the value, there will be no common factor. Okay, so it will uh, create the residue in mod operation independently over 1 by q. Okay, 1 minus from 0 to 1 minus q, it will create the residue independently. So it will be independent now, and this model is the restriction of the hash table. So it can, there are many more functions we can in cryptographic hash function, when we will have the lecture on cryptographic hash function, or I have actually another series of lecture or for cryptography demystified. There we will discuss lot of cryptographic hash function, and we can see those functions created very independently. Okay, so this is universal hashing. Now, what is perfect? Perfect hashing is a hashing where there is no collision. Okay, it is totally collision free. Now, question is whether there exists any perfect hashing. There may exist a perfect hashing, but the paradox is there. So that ensures there will be collision. Okay. So perfect hashing is very hard to find, but a very good universal hashing has some probability to become a perfect. Okay. There are some example of perfect hashing, and we have a newly developed function which is not very much in use, but it is very good. It is almost perfect hashing. Okay. If there is no double loop, we call that cuckoo hashing. Okay. And we will in the next lecture we will cover the cuckoo hashing, which is a perfect. Okay. That's all for this lecture.